Hello and welcome back to Functional PHP 7. In Section 1, we took a brief crash course to examine some of the new features present in PHP 7 and how those are going to be used to make our functional code a lot better. In Section 2, we're going to address the next question that should be top of mind, which is, why should I consider functional programming? If you already do some level of object-oriented code or have been doing it for many years, then the first question should be, why should I consider learning something new? And that's what we're going to try to tackle in this section. Now, as crazy as functional programming might sound, especially in the PHP world, ironically enough, it does do a good job at tackling the non-functional requirements of our application. Functional code tends to be easier to reason about when you're looking at solving the global scope of solving a problem or troubleshooting an issue. It's also going to lead to code that's easier to read and more succinct. The modularization imposed by composition will lead to code that is easier to test. And when you have protection around immutability and side effect-free functions, it also makes code easier to parallelize. Now, this last concern is something that we won't be addressing in this course, but we will be focusing on the first three, and it's definitely something to keep in mind if you wanted to take your functional programming skills onto a different platform. In the first video of this section, we're going to learn the meaning of writing code that is easier to reason about. You've probably heard this term a lot. Functional programming makes code easy to reason about. And what does that really mean? It really has to do with lessening the cognitive load, which means the amount of information that you have to keep track of at any point in time when you're looking or trying to solve a particular piece of code. And this has to do with, are you having to keep track of the state of many variables at once? Are you uncertain about a function's effects, not just to the particular function call that you're doing, but does it have any effect? Does the effect ripple out into other modules of the system? And functional programming really solves this in two ways. One is by eliminating side effects, and the other one is by promoting this idea that programs have to be immutable or stateless. So eliminating side effects is about providing what a function needs to carry out its work and making that available as arguments. So in other words, functions don't need to reach out of their own scope to carry out the work that they need and return and compute the return value. Because as you understand, if you're needing to reach out to other state, then all this global state becomes really hidden inputs into all your functions. And so, that's another way of increasing that cognitive load. The more global data you have, the more the probability of that data being mutated or changing inadvertently, right, by other parts of the system. And so we're trying to isolate that. We're trying to minimize the use of global state, keeping everything isolated into the function. The second principle of immutability is very important as well, and it just simply states that once a variable is declared, its value shouldn't change, okay? Now, PHP does have poor support for immutability when compared to fully functional languages or even to some other object-oriented languages that have keywords to impose different levels of immutability into your variables. We can do this one way or another in PHP. There is some support for it, but most of it will come out of discipline. And this discipline is really up to us as to what level we want to implement it. PHP will make it really easy to assign state into variables and mutate it. But the fact is that functional languages don't really have support for assignment. I mean, why would you assign to a variable if they're not even variables? They're not entities that are allowed to change. So typically, in a pure functional program, the flow of a function happens through composition. So you're calling functions and passing those as arguments to other functions, and they compose, and that's how the flow of a functional program moves forward. And the last two principles that we're going to learn about, the last two qualities of functional programs, are these ideas about equational reasoning and function level modularity. Equational reasoning is more of a theoretical view of how programs are composed together. So we talked about immutability and side effect free, and if our functions are pure and they have these nice qualities, then their output is going to be very predictable. Because remember, everything that a function needs to carry out its job will be given to it as arguments. And so if we can guarantee that the output of one of these functions, then theoretically speaking, we could replace a function call with the value that it produces into an overall expression, and the result is the same. And then this is called the principle of substitutability or replaceability. You can replace a function call by its value in an expression, and the overall expression remains the same. The result is the same. And so that also helps that idea of programs being easier to reason about. And function level modularity is really no surprise. In functional programs, the emphasis is on the function itself, not on the object, although we know that functions are objects. but the main unit of execution becomes the function itself. And so the idea is that using functions, you're going to decompose big programs or bigger functions. This idea of the monolithic function goes away. And you're going to compose that, split it up into nice small chunks, and then recompose those together to form the entire solution to your problem. So when considering functional programming, you really have to embrace the idea of eliminating side effects at all costs. And some forms of side effects are things like sharing global data, writing UI or to a console or to an HTML page. Also database and file I/O operations. Throwing exceptions is even a form of side effect because the program has to unwind and the instructions flow is broken. And there are functional ways to address each of these concerns. We're going to learn about those later on in the course. The most mundane example that you can think about when thinking about side effects is two functions that share data. And this is something that we do a lot. So consider the figure on the right where the first function do work runs and it causes a change into this global external data. And because it's reaching out to an external resource, this is a form of side effect. And then do more work runs afterwards, and it depends on that data. And so the execution of do more work is dependent on this global data being set. And so inevitably you have a form of coupling between do work and do more work. And so what we want to do is decouple these and make these isolated functions that don't depend on each other. So the other form is of making programs easier to reason about is this thing called equational reasoning. And so the idea is that we have a monolithic program, and you can imagine this to be any type of any big function. And through equational reasoning, if you have functions from one type to another type, again, they always return values. A program is made up from the combination of these functions, f, g, and w. But if these functions return x, y, and z respectively, then when solving this program, you could theoretically replace x to substitute for the function f, and the result of the expression remains the same. Okay, so functions and their values are replaceable or substitutable. And so now when we begin to extend all of these concepts into function level modularity and learn that the programs are made up of the sum of its parts, then now we can translate the theory into this concrete example where we take a function that computes, that reads the files for all the Nobel Prizes that are being awarded, and it finds the most decorated Nobel Prize category. Then we can consider this monolithic function to be the sum of much smaller set of functions, almost like a cooking recipe being followed step by step. And this theoretical model we can translate into a concrete model, into actual PHP code. And we haven't still seen how we're going to get there, but this is the goal of the first volume. And so we will be able to solve this example just like the function I've showed you here. If you take a closer look at this code, you really don't see where the actual execution is happening. Actually, all you see is basically a list or a recipe of functions that need to be executed to solve this problem. And that's exactly what declarative code is all about.